So we're going to run through some stuff on the laser ablation system for a demo purpose. So this is going to be a little different than a training. So an actual training on this takes about 3 to 5 hours, depending on the complexity of the system and all that jazz. But we are going to go over the very basics, not necessarily how to get there, what buttons to click all the time, but we are going to try and cover this as in detail as makes sense for, say, a class or something like that. So the ICP-MS software is called Icpms Top, and we have configured it for laser ablation. These laser ablation software is just called New Wave Research Laser Ablation. And we're going to turn on the light sources here in a second and find our samples. So we've already loaded up some samples, which are some little BBs, like a pellet, a metal pellet of different types of metals. So we're going to try and see if we can't identify what's in these metals. So the first thing we want to do is ignite the plasma. And so we're going to open up our instrument control panel. So the instrument control panel has a little diagram of our instrument, so it's not to scale, but it shows us the general layout of things, and it has all these little gauges which you can click and hold on. The ones that aren't green have no data because they're not actually being used yet, but we have like the pressure gauge of our vacuum system giving us 1 × 10⁻⁵ pascals, and the pressure gauge of our roughing pump giving us 9 × 10⁻⁻1 pascals. So to ignite the plasma, we're going to hit ignite plasma. We need to make sure that our water chiller is on because that is this loop here that is crucial for cooling down the RF coils as well as the interface cone. And then we need to make sure our argon's on because we need that for the plasma as well. So we're going to hit ignite here. It's going to ask us if our instrument exhaust is working. We're going to hit yes. Because we know it is, and this is for liquids specifically, so we're going to skip this. And we're going to do a little time lapse here of it igniting because it takes a little bit. All right, so we've got the helium gas flow up for the laser, and consequently we've also found the laser on the surface, or the surface of our sample in the laser window. It doesn't look very easy to see. It's not very visible, and that's mainly just because of the lighting. So hopefully we can fix that a little bit, make it a little easier to see. In the meantime, we're going to look at the ICP-MS software. So we need to load up our method. So I'm going to do that right now. And our method is basically just telling the instrument what to do for a single acquisition. And so this just tells it what masses to look at. So we'll load up this method and then I'll show you what I'm talking about. So we're running the system in spectrum mode. So the main modes that we run in are spectrum or time resolved. So in spectrum mode, it's just going to collect a single mass spectrum with the settings we tell it. So what masses and how long to integrate for, and then how many duplicates we want to do, replicates. The other option is time resolved, where it'll acquire a set of masses, whatever we tell it, as fast as it can over a certain a certain length of time. So it'll give you a signal versus time plot for each mass. So for this mode, we're going to run spectrum because the sample is homogeneous, so we should be able to get a decent spectrum for it. And the whole point of showing you this part was just to show you what kind of options we have here. So we can go into our periodic table and we can check out different masses, different elements, different isotopes. So for example, if we double click iron, we'll get the isotopes of iron and their natural abundances. So this is true for any of these masses. You can get an idea of what elements or what isotopes you might want to choose for each element. So for these BB shot samples, we're looking at sodium, magnesium, aluminum, iron, copper, arsenic, tin, antimony, gold, lead, and bismuth. And we're doing it at 0.1 seconds per point and out of our peak pattern. So this would be a Gaussian peak of a single isotope. We will take 6 samples throughout the peak to give us a semi-quantitative distribution of sampling. So that gives us 0.6 seconds per point. And we're going to do 3 repetitions for a total acquisition of 30, we'll round it to 32 seconds. Okay, so we need to time this with our laser. So our laser takes about 8 to 10 seconds for the sample to get from the laser to the plasma and start acquiring. And so we need to time it because we also have a stabilization period for our laser of 10 seconds. So the laser fires with the shutter closed for 10 seconds to make sure that the beam is stabilized before it hits the sample. And so we need to be able to time that, and we need to have a raster that's long enough on with our laser ablating the sample to give us enough sample stream in the stream to be analyzed by the ICP-MS. So I just wanted to show you what that looked like. I also wanted to give you a rough idea of what it looks like in the laser chamber. So it's really hard to see inside this laser chamber. It's really hard to see the sample. And so we'll put it on this coaxial light source, which gives us a nice narrow beam. And then we'll peek through, as you can see at this camera angle, it's quite steep. And we'll peek through to try and get an idea of where the sample is in the chamber. And then we can move around in the software using the motorized controls. So I'm going to try and get our light source to look a little better real quick on our laser sample. Another thing I forgot to mention is that we've let the plasma warm up for quite a while now, about an hour, and that's to let everything stabilize. So that's a step that you guys don't have to sit through, which is kind of nice. So we're going to set up our method to run. And first I need to do some fiddling around in the data analysis panel. So that's something that you don't need to know how to set up. But we're going to get our method ready to run, although we're not going to run it. So this is actually going to be an acquisition. We're first going to run a blank. So this blank would be just the gases flowing and nothing else. No sample from the laser, just gases flowing to get us an idea of if we have any baseline signal for any of these analytes that we're looking at. So usually we'll run one of these blanks every so often. And also you have to worry about bleed through between samples. So you need to give enough washout time for the gases to purge all the leftover sample out of the lines and whatnot, so that there's no increase in background over the duration of our runs. So we're actually only going to run a couple of these lines to give you an idea, but usually you would do several replicates on each sample to give you an idea of, to give you good averages for this analysis. And so we have 4 samples in here, and so we'd probably run at least 3 lines, probably 5 lines on each sample, and giving us 20 total lines, so you can get an idea for how long this would take. But we're only going to run a couple of these. So I mentioned the 32-second acquisition of the ICP-MS, so we need to give the ICP-MS enough sample to work with. So we're going to draw a line, and this line is going to be the direction and distance that our laser scans. So we're going to look at the properties of this line. So it's just a single pass and a scan speed of 10 microns per second. So we need to take into account all the factors at 10 microns a second. So how long does our line need to be? If we have 32 seconds of acquisition, then we need to make sure that our line is 32 times 10 microns long, giving us 320 microns, plus we're going to give ourselves a little leeway, so we're going to probably go up to 400 microns long just to make sure that we have plenty of time to acquire everything we need. The laser settings, this is an advanced thing to mess around with. Not really mess around with, but you need to determine the optimal settings for a specific sample because all samples ablate differently. And so we're going to run this at a 55 micron spot size with a power of 60% and a repetition rate of 10 hertz. So our laser is a pulse laser, and so it's going to use a pulse rate of 10 hertz. And so we're going to apply these to the laser to make sure that everything's set up prior to running, such as the aperture rotation and whatnot. Okay, and so up top we can see the laser settings. So we set 10 hertz, 55 microns, and 60% power. And then here's the fire button and the shutter. So we can actually fire the laser with the shutter closed, and it's going to not actually hit the sample, but it is firing. And as I mentioned before, you might have seen these numbers fluctuating. This is the fluence onto the sample. As I mentioned, we need to give it a 10-second warm-up time. And so when we go to actually run the scan, there is a there is a 10-second warm-up time down here that's going to make sure that our laser is nice and stable before it actually goes to the sample. So back to the ICP-MS software, we're going to run a blank right now, which again, we're not firing the laser. This is just a blank to give us the background signals for our gases and whatnot. So when I hit OK, it's going to start the acquisition. We see 3 different plots on here. The first one is from 0 to 100 AMU, 100 to 200 is the second, and 200 to 260 is the third plot. It's on a logarithmic scale, so you can see that. And they go from 1 to 10 to the 9, 1 to 10 to the 8, and 1 to 10 to the 7 on the y-axis. And so it tells you how much time is left in each acquisition, and the number of acquisitions is in the bottom left there. So this is taking a mass spectrum, and you can see that it doesn't take very long, 32 seconds. And once it's done, it's going to output the data to our data analysis panel, where we can see our blank number 1 right here, and the counts and the RSD for the counts and the RSD for each of the masses that we're looking at. All right. And so if we wanted to look at the mass spectrum, we could. If we expand this, it'll help us a bit. But the mass spectrum can be a little hard to see unless we change the scale. There we go. To a logarithmic scale. So there's a difference between our 2 plots, so the acquisition plot versus the plot that we're seeing here. On the y-axis has a different scaling, and that's because this is in counts per second, and so it's normalized to time, so these are a little smaller. The peaks are a little smaller. And so these have been averaged. There's 3 replicates. They've been averaged up into these counts values up top. And so, like I said, we're only going to run a couple different lines to give you an idea of how this works. And then you can basically imagine sitting here and repeating this process over and over. So it's time to run our first line. So we're going to call this line 1. You'd probably want to do something quite descriptive. And we're going to hit run method, and it's going to take us to the dialog box directly before the method is run. Now, there's some timing here, as I mentioned. So there's 10 seconds of laser warm up. Then there's 10 seconds that it takes the sample to get from the laser to the ICP-MS for detection. So we need to time 20 seconds from when we hit run on the laser, and then hit run on our ICP-MS. So you're going to see the laser run. So there's our 10-second warm-up time. And so it is firing, but the shutter's closed, and now the shutter's going to open and begin the scan. You can see the material ablating away in the center of the camera. And now we're going to start our ICP-MS acquisition. Hopefully we see signal, lots of signal. That's good. And hopefully we have enough sample. If we did our timing right, we have enough sample going from the laser to the system to finish our acquisition. And don't forget, there is 10 seconds of additional sample in the line from when the laser stops. So we have a few seconds of delay. We should be fine. And the acquisition is completed, and the timing worked out pretty well. So if we go look at our actual line sample, all the counts, well, not all the counts, because not every shot that we're looking at has the same masses in it, but most of the counts increased. Specifically on this one, copper went from several hundred to tens of thousands of counts. Arsenic went from 20 counts to 600,000 counts. Tin went from 100 to 1.4 million counts, and so on. So this is giving us an idea of the background versus the signal of the sample that we're looking at. And we can look at the mass spectrum for these as well. It's nothing more special than the one that we looked at before. So we're going to run one more line. And so we have to close the run box over here. And then we don't want to run the same line that we just ran. So we're going to move it over. And we want to move it over far enough that we're not going to have to worry about the two trenches overlapping each other. And so there's a lot to do with focus on this because and this sounds weird, because the laser is focused in the same plane as the camera that we're looking at. There is a beam expander and a beam condenser in this laser, and so it does actually have a focal point. And so we need to make sure that as we adjust our focus, we move the line into the correct Z position. So we're going to give it a couple minutes to wash out. So we need to make sure that the sample has had enough time to clear out of the lines from the gas flowing through it. And then we'll start our second run. All right, so with adequate time passed for our washout, we're going to begin our second run. And so this is very repetitive from the first run. We get our ICP-MS ready to acquire. We begin our laser scan in the new spot that hasn't been ablated before. So the helium gas is going to carry this over into the ICP-MS. And so we need to wait 10 seconds for the sample to make it from the laser to the ICP-MS. And then we can begin the Icpms acquisition right now. So we're going to do this, like I said, about 10 to 20 times, depending on how many samples, how many lines you have to do. You can also drill down into a sample, so you can just hold the laser in one spot and see if there's any difference in depth profile, or if you're just trying to do very fine analysis, such as on geologic samples where you're looking at maybe micro-inclusions or just small little crystallites inside of a larger structure, then you can just do little spots and acquire them that way. So again, we've seen this is the same sample, so we see a similar increase in metals between the blank and the sample that we ran. And so we can export this as a CSV or an Excel sheet or something like that. So this is about all that you would do, except again, repeating the process over and over to acquire data on the laser ablation system. And so we're going to go through the process of shutting this down, which is the reverse of what we did to set it up, and export the data and clean everything up. So thanks for watching. Let me know if you have any questions.